Hello everybody. So we are going to solve this example to apply what we discussed before on the degrees of freedom. It's going to be a very good practice to apply what we discussed and to understand how to count the number of variables, the number of equations, and all the things that we discussed in the previous video. So this example here, it's a very simple example. We have a mixer uh, that mixes two salt solutions. So I have here stream number 1 and stream number 2. These are two salt solutions that are being mixed in this mixer. It's just a tank that and there's a motor that rotates the shaft with the impeller, and this impeller rotates to mix things. So it's just a mixer. It doesn't matter how it looks like for now. And we are told that given that the flow rate of the product stream is 1.5 times the flow rate of the second feed stream. So this is an additional relation that we can use, and we'll come to it later. And it's desired to produce a solution with concentration of 11.8 mass percent sodium chloride. So this is the mass percent of the product that we have here in the problem statement. And we are asked to first perform degrees of freedom analysis on the process and decide whether the available information are enough to calculate the missing parameters, and then to calculate the missing flow rates and compositions. So what we're going to do now is to first, before we do the degrees of freedom analysis or perform the degrees of freedom analysis, we have to make sure that the flow sheet contains all the information. We mentioned before that we have to have all the components in all the streams, whether we know their values or not, and the available information, flow rates or compositions. So we see here that this stream contains all the information that we have, the same for stream 3, but we don't have anything in stream 2. We know that the mixer mixes two salt solutions. So this is a salt solution, and this is another salt solution, which is a mixture of water and sodium chloride. So we need to have this on the diagram. So these are extra information that we have to have on the flow sheet, and we will see now why this is important. So for the first part, when we before we do the degrees of freedom, we have to make sure that we extracted all the important information from the flow sheet, from the description of the process. So one thing that was there is that the flow rate of the product stream, which is stream 3, is 1.5 times the flow rate of the second stream, which is stream 2. So it's a relation between two parameters. These two parameters are the flow rate of stream 3 and flow rate of stream 2, and the relation is, this is 1.5, it's not 2. It's a mistake. So this is M3 is 1.5 times M2. So when we do the degrees of freedom analysis, now we can fill in the blanks. So we have number of variables minus number of given variables minus number of equations minus number of additional relations. For the number of variables, we said that the number of variables is the sum of all the variables in all the streams, and that for each stream the number of variables, independent variables, is equal to the number of components. So here I have two components. Here we have 2, here we have 2, so it's going to be 6. The number of given variables is, and again, for the number of variables, we are just here, we are just counting. So again, I want to emphasize this point, that we are just counting the number of variables. It doesn't matter if these variables are the flow rate and the composition of one of the components, or it's the two flow rates, or whatever the two components or the two variables that we have, but they have to be two independent variables. So here 2, 2, 2, so it's 6. The number of given variables, again, the given variables which are the independent variables. So I have here a flow rate, so this is the first. We have here the mass percent of sodium chloride, so this is the second, and that of water. So this number is dependent on the previous. So if I'm not told that the water percentage is 75%, or the water concentration is 75%, I can know this by myself. So this is a dependent variable, so we don't count this. So we have 1, 2, and again the same here, we have one of them to be counted. So we have three given variables. So we have 6 variables, 3 of them are given, and for the number of equations we have 2 components. I can write an equation to do the mass balance on sodium chloride and equation to do the mass balance on water. So we have 2 equations. So this is 2, and the number of additional relations is 1. We have only 1 additional relation. So when we put everything together, we have 2 plus 2 plus 2. The 3 streams, each one contains 2 components. The number of given variables are 3, number of equations is 2, number of relations is 1, so degrees of freedom is 0, which is good news, which means that the problem is solvable. So we can proceed with the solution with confidence that we have all the information needed. Here, this is the addition relation. It's correct relation. It's not the previous one. So back to the degrees of freedom, there is something that I want to mention here, that when even the degrees of freedom is not done yet, we can still make use of the degrees of freedom by looking at the terms that we have. So we agreed that these 2 terms combined represent the unknown variables, which is the variables that we want to calculate, and these are the equations that we can use. So I have to keep in mind that I have 2 balanced equations and 1 additional relation. So these are the equations that I can use to calculate the missing variables. So what I'm going to do now is I'm going to list all the equations that we have, write them, and substitute with all the known variables, and then we will see how to use them all. So we have balance equation, total balance, which is M1 plus M2 equals M3. We know M1, but we don't know M2 and M3, so this is the first equation. The second is the balance on NaCl, so the mass flow rate of NaCl in 1 plus 2 equals 3. We know that in stream 1, 25% of the flow rate. I don't know anything about the NaCl in stream 2. I know the composition in stream 3, which is 0.118 multiplied by M3 dot. For water, it's going to be very, very similar. 75% of the flow rate of stream 1 plus the water in stream 2 equals the 88.2% of stream 3. So this is the third equation. Of course, these are not 3 equations. These are 2 independent equations and 1 dependent. So we will pick any 2 of them according to which are easier for us to use. Finally, we have the additional relation, which is this M3 equals 1.5 M2. So we have 4 equations. We need to pick 2 of the first 3 and the 4th one. One thing which is a very important skill that you have to acquire when you solve these problems is to be able to pick the equations that would be easier to solve together. In general, you can pick any 2 of these 3 and this equation, and you can use them to solve 3 equations and 3 unknowns. But you can do this in an easier way. For example, you can see that this equation contains 2 variables, M3 and M2. This contains M2 and M3. So these are 2 equations and 2 unknowns, so you can use them directly to solve or to get the values of M2 and M3. This is going to be much quicker and much easier than solving 3 equations and 3 unknowns. So you can solve it by taking M3, equation 2, 3, and 4. Still going to produce the same result, but this is going to be 3 equations and 3 unknowns, which is not something fun. So we can use equation 1 and equation 4 to calculate M2 and M3 directly. So this is what we are going to get. And now we can substitute in equation 2 or equation 3 to get the mass flow rate of sodium chloride in stream 2 and of water in stream 2. And from them we can get the mole fractions of water and salt in stream 2. So this is a good example for a problem that we can use to learn how to do the degrees of freedom analysis. In the next video, we will solve one more example, and we will put some systematic steps so we can make sure that we don't forget anything when we solve similar problems. So I'll see you next time, inshallah. Goodbye.